Swayam Prabha. Digital India. Educated India.
How many of you are here? 30, yeah? Huh? 30? 36. Big class. You're all in 11th, 12th standard? 11th? All 12th? No 11th? 11th going to 12th. Okay. 11th going to 12th. Okay, so very good. So while they will take some time. Vandacha? Okay, so you open that. Yeah. So let's see. You have had several lectures today or yesterday also, or today? Yesterday started yesterday, right? Oh, day before yesterday. Oh, okay. So what were the lectures that you came across? Any spectroscopy lectures were there? What were the lectures? Just name a few quickly. Electrochemistry, quantum chemistry, quantum mechanics. Who Mangal Sundar taught you that? Okay. Biotechnology. Protein folding. Organic chemistry. Eigenvalues, eigenvectors. Okay. All right. Mechanical
physics a little bit.
Okay. All right. Yeah. Okay. So, okay. You just cancel that. No. Okay. Fine. So just to. All right. So this will work. So all these lectures, they brought their own laptops, is it?
Yes.
Oh, I see. Then they put it like this. Then why is he struggling? He should have mastered it by now.
Some didn't have presentation.
Some
lectures didn't have presentations.
Then they spoke. Okay. All right. So there are different. So what I am going to talk to you. Yeah, it works, right? Fantastic. Very good. Thank you. Thank you so much. Yeah. So that is my name, and I come from chemistry department. The topic I am going to talk to you is photoemission. Right? That tickles you something in your mind? What is that? Photoelectric effect. Right. So the starting point is photoelectric effect. Okay. So in 1905, people Einstein tried to explain that using HNU is equal to kinetic energy plus binding energy. Right? Photoelectric effect. So based on that, there is a spectroscope which is developed. Okay. So that's what I am going to talk to you today. So these are some books. You don't need to worry about it. Okay. So I'll just give you some background. What is this XPS instrument? How does it work? Then something called Auger electron. Electrons are different, or all electrons are same? Electron is electron, right? You have different electrons, green electron, blue electron, all the electrons are electrons, right? The origin of this, there is a electron called Auger electron, and then how do you actually catch these electrons and study their kinetic energy? Then this expression you already know, kinetic energy plus binding energy is equal to HNU from photoelectric effect, correct? And then you have this, I'll give you some spectrum, something about these things, this XPS interpretation. Okay, all right, and then some examples and XPS technology. I think I'll have some few slides on that. Okay, that's what I'll going to cover. So normally, when we have solids, so we have solids, liquid, gases, right? We also have, of course, plasma also, but solid, liquid, gas are the ones which we deal with. It contains atoms. All of them contain atoms. Atoms contain electrons. Also, they contain nucleus, right? So, suppose if we remove an electron from an atom or from a molecule, if you can actually this electron, where it is coming from, it will have a memory. That is nothing but your photoelectric effect, basically. Okay. So, if you can actually deal with that, look at that electron and try to analyze its energy, then we will be able to say where it is coming from. Now, let us look at solids. Let us say this is a solid. I have a solid. Now, I want to see what this solid contains. This solid, what does it contain? It contains carbon, it contains oxygen, right? With the table in front of you. Even a paper you see this, it contains carbon, contains oxygen, it may contain other elements, right? How do we know that? How do we analyze it? So, to analyze that, there are several ways of doing it. People actually try to use neutrals, ions, electrons, photons, all of them, they impinge on the surface, and then something will come out of that. You see here, if the molecule, it vibrates. So, you can actually look at that in IR. There are a variety of ways, but don't worry about all that. What we are going to look at is this one. So, if you have photons going in, photoelectric effect is basically photons going in and then the electrons come out. So, that gives you XPS, photo emission spectroscopy. Okay. So, that is the one which we are going to look at. So, what is in photons, what is out? Electrons. Okay. So, that is what we will look at now. The background is, it's based on Einstein's idea about photoelectric effect. He explained that in 1909. Okay, where you shine light, you get electrons. He explained what is the energy of this electron with respect to the light that is shined, and how it is related to the binding energy. The electron has to be sitting in an orbital. Orbital has a particular binding energy or a particular energy. We call it as binding energy, right? So, the binding energy and the kinetic energy, the electron comes out. These two add. If you add this, that should be equal to conservation of energy. Should be equal to h nu, right? So, that's basically what he explained. Now, till 1905 to 1960, this photoelectric effect, people were working, but then they were not able to convert into a spectroscopy. There were a lot of hurdles because the technology was not sufficient, right? So, it took nearly 50 to 60 years to convert this into a spectroscopy technique. So, what is spectroscopy? Spectroscopy is, use a probe, a electromagnetic radiation, send it to the molecule or a solid, right, and then it will interact with the matter. It can be a solid or liquid or gas, and it will come out. Some of it can get absorbed, or it will lead to some changes in the material. So, what comes out, you measure that property, and then there will be a difference. What is going in and what is coming out, there will be some difference in energy wise, right? And then if you can measure that, then you know the property of the molecules or atoms or solids, etc. Okay. Now, 1960, around that time, this Sigmund developed this spectroscopy, photoemission spectroscopy. There are variety of spectroscopy techniques. You take molecules, for example, molecules rotate, vibrate, translate. All these things can be measured. The energies of all these things can be measured using spectroscopy techniques. And this is another technique which measures the binding energy of inside the atom. Okay. So, then because he worked on that, and then he got Nobel in 1981. So it took, see how much time, it took 75 years to get a Nobel Prize in that. That's one's age, right? Right? People, those days, they were not living even 75 years. They were living only 50 years. Right? Today we are living at least, average at 80 years. So they worked on that. So this is the photoelectric effect that you know. Right? So you have a photon of frequency nu, for example. This is the photon energy, that is the kinetic energy of the electron that is coming out. So if the photon energy matches with the threshold frequency, threshold energy, and then you start seeing electrons coming out. If it is less than that, even if it is intense photon, you will not be able to eject electron. That is the photoelectric effect. And then the frequency is proportional to the kinetic energy. You see that, as you increase the frequency, kinetic energy is also increasing linearly. It is supposed to be like that. Right? So this can be written as, for example, this point is nothing but work function if it is a solid. If it is a solid, if it is a gas, it is ionization energy. Ionization energy. Right? So now suppose if it is more than that, then you start seeing kinetic energy here, some kinetic energy there at this value, you have some kinetic energy, right? So the h nu is equal to half mv square. This is the kinetic energy term of the electron plus phi. Phi is the work function or nu t, which is basically right. That is our photoelectric effect. If it is a gas, as I said, it is ionization energy. So you ionize the electron from gas, means it can be an atom or a molecule. You ionize that. So electron will come out with this energy. So this is what we measure. This is what we basically measure. Okay, see the interesting thing is cesium metal work function is very low. What is work function? Remove the electron. So you can remember that. So for cesium metal, work function is very, very low. It's around 2 electron volts. Right? So if you have a UV light, you shine on that, immediately electrons will come out. Electrons will come out. Whereas other metals, the work function is a little large, a little high, 3 electron volts, 4 electron volts. So you need to have UV light will not be sufficient. You have to have higher energy, X-rays, soft X-rays, etc. Right? So this is what is given here, work function. These are all different work function values. See, cesium is the lowest one, 2.1 electron volt.
What is phi in solid?
Work function. Phi. Work function. They would have given, that Einstein's expression, work function is there. No? Okay, maybe they wouldn't have given you that. They wouldn't have given you that. Kinetic energy is equal to h nu minus binding energy. That's what probably they would have taught you, right? They didn't give a work function there. They gave work function also? Yeah. So if it is a solid, it is work function. If it is a gas, it is ionization potential. Work function is qualitatively, I remove an electron from here, I send a beam of a photon and then I remove electron. When the electron comes out, it leaves a positive charge behind. So the positive charge will not allow the electron to come out so easily. Right? So the energy required to overcome that positive charge can be termed as the work function. Once it goes out of the influence of that, then it is free. Right? You can call it as a work function. Okay? There are ways of measuring work functions. All right? Okay? So you have X-rays. There are liquids also you can do, but liquids require special equipment. Normally what you do with solids, you cannot analyze gases. Gases is a different spectrometer, is a different instrument, same photoelectron spectrometer only, but for gases you have a different one, for solids you have a different one, liquids also should be different. Ionization energy. Ionization energy.
The method of photoelectric effect, will it
that will not be different. That is same, right? You send a photon, you remove electron. This may be solid, liquid, gas, right? It can be, or even atom, right? So that is remain same. But in the labs, in IIT now we have 3 or 4 electron spectrometers. So there you will have an X-ray energy of 1253.6, 1486.6. These are the X-ray tubes which are present in the, which are fitted to the spectrometer in the lab. So this energy is fixed. You see this? This is a monoenergetic beam because HNU has to be fixed. HNU cannot be different. HNU has to have a precise value so that you can measure the binding energy. Correct? So the HNU, the magnesium K alpha photon, this is actually there will be a target, where they bombard X-rays and they get photons out. Those photons are these two. They have a precise energy, right? So what you have here is, in this case, can't clean this, sir. Oh, you have to. So you have of course you have phi also here, but let us not worry much about it now. So this HNU has to be known precisely. If you know this, this is something you can measure. If you measure this, if you know this, so automatically you know binding energy. Binding energy of the electron sitting in, for example, 1s orbital, 2s orbital, they have to have energy. That energy is the one which we are actually measuring. So we are talking about 1s orbital, 2s orbital, 3s orbital, so on and so forth. What is the experimental evidence for those orbitals? Can we measure the energy of those orbitals or energy levels? So this is the experiment. Photo emission is the experiment. Okay, we all study that, right? So this has to be precise. So that's why these values are fixed here: 1253.6, 1486.6 electron volts. All right. So that's why they call it monoenergetic X-ray beam. That's what is used in the experiment. Magnesium, Mg is magnesium, Al is aluminium, K alpha is the electrons, the X-rays are coming out from, K is actually K, and K is basically X-ray notation for 1s orbital. X-ray notation, because you are not familiar with that, but this K mean K, L, M, these are all X-ray notations, because this you are actually generating X-rays. So that is the reason why they use K instead of 1s orbitals. Okay, so it's basically X-ray notation.
Does this notation have anything to do with the Bohr model where they have KLM mentioned?
Sir,
You can say that, of course, yes, you can say that, but yeah, you can say that. K is basically 1s electron now, we know that, right? So X-ray notation, normally they say KLM, but this is also related to that. Yes. Okay, right? So basically
Sir, you had explained about XPS. Does the X in XPS stand for X-rays? The X in XPS.
X-ray, photo electron spectroscopy, which is also called photo emission spectroscopy.
Okay, sir.
Photo emission spectroscopy has two
Subtypes.
One is X-ray photoelectron spectroscopy, other one is ultraviolet photoelectron spectroscopy. I'll just come back to that point later. Okay.
Thanks.
All right. Now the point is, since you have asked that question, I will explain that. So this is the, let us say, an electron, the atom. Let us say this part is your nucleus. It has electrons, neutrons and protons, and you have electrons here. So these are all shells. These are all shells. So you have electron here, you have electron here. These are the electrons. This is not a correct model, but it's only a representative. So if you use X-rays of what the energies I have told you, 1253.6 or 1486.6 electron volt, you can actually go almost to the core and remove this electron. If you use UV light, you remove only these electrons. These are valence electrons. They are less. Their binding energy is less. So using less energy photons like UV photons, you remove electrons from the outermost shells, which are nothing but valence electrons. If you use X-ray, this is also not hard X-ray, it's a soft X-ray. So it will remove electrons from the core electrons, core. That you should remember now. So once it is removed, this is a free electron. It is a free electron, right? Okay. So it leaves a vacancy here. It leaves a vacancy. The atom becomes unstable. The atom becomes unstable. There is a vacancy there. There is a hole. Right? Now, look at this picture. The same thing I have drawn in a different way. Let us say you have 1s, 2s, 2p and so on and so forth. You have energy levels. You have these energy levels. See that? And then as you keep going up, if it is a solid, when atoms come together, the valence electrons start forming band. The valence electrons, not the core electrons. They overlap, right? They overlap and form a band, metallic bond. Call it a metallic bond. You have heard of metallic bond? That metallic bond, in metals, they form a band which is continuous energy. It has continuous energy. Here it is very well defined. You see this? The energy is very well defined. 1s, 2s, 2p very well defined. But when you go to valence levels, where all the valence electrons come together and then they form a band, the energy is not well defined. The electron can belong to any atom. Like a sea of electrons. A sea of electrons will give you kind of a valence band, or this band what you are seeing. But the core electrons confined to the core, the nucleus of that particular atom. They are actually bound to that. Are you seeing that? Suppose I am saying there is a core here, there is an electron here. This electron is highly influenced by the core. But if there is an electron somewhere here, little far away, it is very mobile. It can interact with other electrons and form a band there. So they are all mobile in that band. But whereas this one cannot be moving around. It is very close to the core. It is fixed. Its energy is fixed. So here you have these levels are specific, whereas this forms a band. Now if you use X-ray photons, you can actually remove these electrons, any of these electrons, and that electron carries the memory of which atom it is coming from. Right? It carries the memory. Oh, I am coming from this atom. That atom can be any atom in the periodic table. Did I bring my cell phone here? Oh, okay. So, I can't do anything now. Yeah. So if you actually remove this electron and then try to measure the kinetic energy of that electron, you analyze that, then you know this energy, you can calculate the binding energy of this core electron, any of these core electrons. The moment I calculate that binding energy is specific to that particular element. So immediately this element is present in the sample. Right? Whereas these electrons will not give you that information straight away. Because they belong to they can belong to any atom, because they are mobile, they are in the band. Okay. Now, but then you can actually eject these electrons also. You can ionize these electrons. That will give you ultraviolet photoelectron spectroscopy. You use this energy is in the of the order of 22 of the order of 22, let's say 40 eV roughly. Can be even little more also, but that is the energy. Whereas X-ray is EV. That one 1253.6 and 1486.6 eV. So this is the photon energy to remove electrons from the core levels. This is the energy which would be sufficient to remove electrons from here. Both are photo emission, but one is, since X-ray is used, it's called X-ray photoelectron spectroscopy. The other one UV light is used, so it's called UV photoelectron spectroscopy. Okay. But then once the electron is removed from here, this atom becomes very unstable. It's excited state, right? So what happens is some electrons which are sitting in the higher levels, they can jump into this to relax, for the atom to relax, and that leads to some energy difference which will come out as X-ray. It will come out as an X-ray. For example, here, see, this is the hole. This electron is coming from here to here. That energy, this energy, is the energy that is used by this electron, and it will come out. Okay. So you have the energy levels 1s, 2s, 2p. Consider only these three. But if you go to a transistor metal and then then you have to deal with the d electrons, f electrons, and all that. Right now, the simple ones is 1s, 2s, 2p, etc. Right. This is something like nitrogen, carbon, oxygen. We deal with that. But if you go to transistor metals, rare earth metals, then you have to deal with the f electrons, d electrons, etc. So this electron comes down, and that energy is now picked up by this electron, and that electron comes out. That is called Auger electron. Auger. That is called Auger electron. So there is a spectroscopy based on Auger electron also. Okay. So you have X-ray photoelectron spectroscopy, ultraviolet photoelectron spectroscopy, Auger electron spectroscopy. Okay. Got all this idea?
Sir, how do we tell whether the electron we are analyzing is an Auger electron or like
Yes. Okay. Yes, there are ways of distinguishing that. Yeah. So maybe I can answer that question right away here. For example, you remove electron from here, and HNU is the energy you have used. This is the electron energy that you have measured. So it is a one electron process. It is only one electron process that is coming out. Whereas here, 1, 2, 3 electrons are involved. It is a 3 electron process. 3 electron process. To answer your question, in this expression there is HNU, but in this expression there is no HNU. Right? So if you change HNU, then what will change in this expression? Which one will change? There are 3. I am changing this one. This is fixed for a fixed element, for a particular metal. So I change this one. What will change now? This will change. This will not change. This will not change. That is fixed. In a given atom, particular orbital will have energy which is fixed. This will change. So that way, you change the photon energy. You can say it is coming from X-ray photon, photo emission photoelectron or Auger electron. So in the case of Auger electron, it will not change at all. The energy that you are looking, this energy will not change even if you change the photon energy. For example, I can take X-ray aluminum K alpha and then magnesium K alpha, record the spectrum. If it is a Auger spectrum, it will not change. It will come to exactly the same kinetic energy. But if it is a photoelectron, then it shifts because the kinetic energy is different. Huh? This one. Auger electron. OJ electron spectroscopy. OJ electron spectroscopy.